Hello, I'm Vanessa, your Tubemaster host. Global leaders and thoroughbred horses aren't the only things to come out of Kentucky that are fast. Today, we're going to talk about pressure drop testing, often referred to as DP testing or delta pressure testing in the industry. We're going to share with you the top 3 concerns we've discovered from our customers for pressure drop testing and introduce actual tools we deploy on the job to deliver on those concerns. Saddle up, because today, Dr. Paul Gosen is your guide to mastering your catalyst change process. Dr. Gosen serves as Tubemaster Research and Development Manager. Paul, you're at the gate.
Pressure drop testing comes at the end of the catalyst change. At this point, the reactor has been unloaded, cleaned, inspected, and reloaded with fresh catalyst. We are measuring the pressure drop of a very controlled stream of air through each catalyst tube individually. Those measurements guide us to tune the reactor so that at the end of the job, the pressure drop of each tube is within a narrow specification range. This step helps ensure that when you run the reactor, all reactor tubes perform safely and consistently. I'm going to list these concerns in priority order. The order I've put them in is from our experience with ethylene oxide, or EO, reactors.
What tubular reactor types are you responsible for in your job? We've included a quick poll here so you can tell us what kind of reactors you have. Go ahead and fill that out now. Your priorities could be the same as our list, maybe in a different order, or maybe one is not important to you at all. Our Tubemaster team would be very surprised if none of these concerns applies to your reactors.
Let's jump right in. We're going to do this as a countdown, starting with priority number 3 for pressure drop testing, which is speed. Okay, that's the obvious one. When you are in the middle of a catalyst change job, you can feel the constant attention to meeting schedule. Not surprising, every minute the reactors are not running, you have lost an opportunity to make money. It's also not surprising that Tubemaster would put speed on this list. Tubemaster made its name by having the fastest pressure drop testing system in the industry, twice as fast as other methods. In fact, our top speed record was made by the joint Anabeeb Tubemaster team when we completed pressure drop testing of 100,000 tubes in 18 hours. That's an astounding 5,555 tubes per hour. But why is speed at the bottom of the list? Because we can't let speed be a distraction from what's more important than speed. The safety of our people is more important than speed. The performance of the reactor, once the job is done, is more important than speed. We want to be fast, but we don't want to be in a hurry. How do you get fast pressure drop testing without being in a hurry? Speed has to arise as a natural result of the design of the pressure drop system. 2 features of a pressure drop testing system naturally give operators a huge speed boost. The first is a multi-tube test device. At Tubemaster, our pressure drop test devices measure up to 10 reactor tubes at a time. For typical EO reactors, we run 4 devices simultaneously, allowing for 40 tubes to be tested at a time. The second feature that allows for speed is a high degree of automation. For our pressure drop test devices, an operator inserts the rack of 10 tubes into the reactor tubes and presses a button. The tubes are automatically sealed. A laser rangefinder automatically determines which tube the device is in. The pressure drop test is performed, and data for all 10 tubes is automatically transferred to a central data computer in the reactor. When that computer receives the data, it lets the test device know, and the test device automatically releases the tube seals and signals the operator to move to the next group of 10 tubes. This level of automation delivers a cycle time that is 45 to 90 seconds. So for our example, with 40 tubes tested per test cycle and 90 seconds per cycle, you can quickly calculate that a reactor with 8,000 tubes will take 5 hours to test completely. When you use a pressure drop test system that delivers speed as a natural result of its design, you deliver speed without the operators, supervisors, or engineers having their attention on speed. Instead, their attention can be focused on bigger priorities. What are those? Priority 2 is that the pressure drop tests must be accurate. This priority might seem obvious too. Your target is to have all the tubes in a reactor within a specified pressure drop range. Let's say it's plus or minus 5% of some average pressure drop. A useful rule of thumb is that you would like the repeatability of your measurement to be at least 1/10 of the specification range. So, if your specification range is plus or minus 5%, you want your measurement repeatability to be plus or minus 0.5%. At first glance, that would seem to be an easy task for modern pressure sensors. Unfortunately, it turns out under field conditions, it is actually very difficult to achieve repeatable pressure drop measurements. The underlying reason for this is that the precision of the measurement has very little to do with the precision of the pressure sensor. It has much more to do with the environment inside and outside of the pressure drop measuring system. If you're on a job with Anabeeb and Tubemaster, controlling the environment inside the pressure drop test systems means that you will see a lot of compressor capacity, surge tanks, multiple stages of pressure regulation. Controlling the environment around the pressure drop test involves managing access manways and ventilation inside the top head and bottom head of the reactor to avoid variable pressure noise in those spaces. It might even involve temperature control of your reactor tubes, if possible, during the catalyst change. In spite of all of these controls, environmental changes can still happen. Therefore, you need to periodically check the calibration of the pressure drop test devices. The calibration method has to be sensitive to changes in the testing environment and have calibration routines that correct for those changes. At Tubemaster, we have a calibration standard customized for each reactor. Another component of data accuracy is to remove chances for error that have to do with transferring data. From my own personal past experience managing a laboratory in a chemical plant, even the best technicians will make an error about 10% of the time if they are involved in manually transferring numbers from a test device to a computer. An important component of accurate, error-free pressure drop testing data for your reactor is 100% automatic data transfer from the test device to the database of test results. So far, we've talked about speed and accuracy. What could be left for priority 1? Here, I'm going to get specific to our experience with ethylene oxide reactors. In these reactors, there is one concern that takes our constant attention, for which we deploy a lot of technology, equipment, and training. So much so that we call it the #1 priority of tubular reactor pressure drop testing. It is, don't miss a tube. What does that mean? It means a few things, all of them related. It means 100% of the tubes in the reactor must be tested. In our example of EO reactors, there can be bad consequences when running a reactor if one tube has either too high a pressure drop or too low a pressure drop.
We understand that 100% testing is a priority for some reactors and not for others, so we'd like to hear from you again. We've got another poll, this one asking what percentage of tubes in your reactors do you feel need pressure drop testing? Go ahead and fill it out now. There's no right or wrong answer here. The answer for your reactors depends on lots of factors that are different for different processes.
Now, just measuring pressure drop is not enough. Pressure drop must be tagged to the correct tube location in the reactor. Then, After the first pass of pressure drop testing, you must find and correct only tubes that are outside of the specification range and not mess up tubes that have already passed the specification. So, while the title of this section is Don't Miss a Tube, the more practical aspect of this in the field is don't get lost on the tube sheet, which is surprisingly easy to do. We deploy many tools to empower you and our operators to know quickly and clearly what tube we are testing or correcting on a tube sheet. Some tools are very simple and some are very technical. First, a simple tube map numbering system is critical. In our experience, locating tubes in the tube sheet using a row and tube numbering system works the best. Tubemaster uses our row master numbered plugs, which we place in the first and last tube of each row to mark row numbers. We use a laser rangefinder to count the tubes. We deploy a laptop in the reactor that displays a map of that specific tube sheet with an interactive row tube query feature. Our test devices automatically associate a specific row and tube number with a pressure drop reading and send it to the laptop, which instantly displays the data on this tube sheet map as we are pressure drop testing. This is an important tool for accurately tracking and finding any one specific tube we are interested in at any time during the job. So if don't miss a tube is a concern for you, many tools need to be deployed for the single purpose of correctly locating a tube on the tube sheet.
Our top 3 priorities for pressure drop testing in a tubular reactor catalyst change are: number 1, don't miss a tube. Number 2, accuracy. Number 3, speed. We've shown you the strategies and equipment that delivers on these priorities. They include sophisticated, automated test devices, field-proven processes and routines, and some surprisingly simple tools for not getting lost on the tube sheet. Together, they deliver a reactor catalyst change that performs the way you need it to. Speed, accuracy, don't miss a tube, the winning trifecta of value for you. We'll be back with more great tips on how you can lead using Anabeeb and Tubemaster to master your catalyst change process.